Hello, and welcome to this talk that will be about combining reinforcement learning with some model-based strategy in order to make the result a feasible solution for learning in a few minutes in real-world settings. I'm Della Santina. I'm presenting this work on behalf of my student Kulkarni, who is no more my student. And this work was also done at TU Delft in collaboration with Jens Kober and Robert Babuška that you can see in this slide. So we all know and love the fantastic and inspiring results that reinforcement learning has obtained already 5 years ago. For example, there's the famous AlphaGo, but there are also very interesting results on simulated robots. However, many years passed, and real-world implementation of reinforcement learning to a complex robotics task is still relatively limited, at least compared to these early results. And if you ask to expert in machine learning or AI, what they will tell you is that reality cannot go faster than real time, and therefore reinforcement learning has inherently some limitations in working in the real world, because there is no way to train a system for years. Well, it is of course possible in simulations. This is, however, not true, at least not 100% true. There are some notable exceptions to this rule. The first one is if you are extremely rich. And also it's very important, the failing of a task is not a big issue, is not safety critical, the failing. And if you can do that, if you have mark these two boxes, then what you can do is to set up some large-scale data collection experiments like the one from this other very famous paper of 2018. Alternatively, if you are still quite rich, so you can afford GPUs and workforce, and your task can be simulated accurately, then you can use some sim-to-real strategy to do most of the training in simulation, then do the final mile on the real system. And there is, however, a third case in which you are not as rich as in the previous two cases, or the task is too hard to model, or simply don't want to spend time to model it accurately. I think a relevant case here is the one of having a robot that has to perform some assembly task that is inherently difficult to model from a dynamic point of view, involving closed chains, involving hybrid dynamics, and so on and so forth. At the same time, it's something that in companies, your robot will most often have to do, to perform some task that involves assembly components in limited information, as humans do. And your small, medium enterprise surely does not want to put all the money and all the time to create a very big either simulator or campaign of acquiring experimental data. But let's be more precise. What we are trying to do in this work is, of course, a very first step in this direction. And what we have here is a serial manipulator, and we assume that we can only measure joint torques and sensing the angles. And but on the other hand, we don't assume any vision input, any knowledge of the state, apart from some rough estimation of where the objects should be placed. So of course, if this estimation is perfect, then the task of inserting is typically quite simple, as you can see on the right. But what we want to do is to generalize, to be able to deal with uncertainties in this real goal position and be able to react to an unexpected interaction with a completely unknown environment apart from the goal position. Of course, when Padmaja first came to me, telling me about this problem, the research problem, as a really supportive supervisor, what I told her was, this is not interesting. This has been solved 15 years ago with model-based strategies. And what she answered to me was, impedance control will not work with this level of uncertainties. Which again, as a very supporting supervisor, what I told her was, I don't believe you at all. You must prove it. And she did. So these are just some videos, but we will provide later a statistical characterization of the fact that within these level of uncertainties, there is most often than not, the impedance control is not enough to complete this task successfully. And this is just another video for an hanging problem rather than an insertion problem. So Padmaja worked on it. a lot, and in the end, it came out this very interesting architecture that we proposed to solve the problem. And let me quickly guide you through the main components of this block. So you can see here two rules of information that represents a very standard, I mean, still advanced, but well-known Cartesian impedance control. So you have a standard strategy on the top left, and then you have, which is feed-forward, and then you have the usual closed loop that implements the Cartesian impedance controller. First thing that we do here is pretty straightforward. We say, okay, if the standard strategy by itself and the Cartesian impedance controller does not work, let's, instead of throwing everything away, let's just try to correct this behavior a bit. So, and instead of correcting at the level of torques, which of course would have been quite hard, we use the power of generalization and abstraction of the impedance controller to add the residual part directly at the reference level. However, this straightforward idea had to be completed with two small but very important changes or addition. What this block does is to look at the time we are in the execution of this task and give all authority to the nominal path, the nominal strategy, if we are at the very start of the task, and all the authority to the controller if we are close to when the nominal strategy should reach its end. And then from there, keep giving the authority to the learning part. So why this is important? It's important because in this way, we know when we are, first of all, when we are far enough, typically just moving towards the goal, even if it's not in the right position, is the right thing to do. So we don't want the reinforcement learning to explore that part, to optimize for exploring that part, and possibly bring us far from the optimal controller with this exploration. Second, we want that if we are in those fortunate occasions in which Cartesian impedance control is already sufficient, then for when the reinforcement learning part starts kicking in, we are already close enough to the final goal, and so the error, the reinforcement learning would see very small errors and will not try to correct. And a second bit is to recognize that this kind of tasks are, this kind of reacting to unexpected behavior is something that it requires reasoning about time. So this is for the reason why we went for a recurrent network as an approximator of our RL strategy. This is what happens after only 5 minutes of real-world training in the same condition that you have seen before. The robot is able to solve the task, and it learns this kind of oscillating strategy in order to bring it outside the region in which it's stacked. And by the way, it learns to bias this exploration in the right direction over time. And I want to stress again, this is 100% based on only torque sensing at the joint level. So, and this to show you how this learning evolves. So again, 3,000 steps is here corresponding more or less to 5 minutes. And what we test here is this average success rate and its variance, and the time steps required to execute the task for the bare impedance controller on one hand, in purple, the full strategy on the other hand. And then we try all the possible combination of learning, of reinforcement learning with impedance controller, with the decay technique, with the residual, with the recurrent part, and then of course our strategy. And quite interesting, I think, what we can see is that in our setup, the impedance controller has roughly 4 success over 10 trials, so it's 0.4 over 1 of success rate. But interesting, if you just introduce the obvious thing, so the residual TD3 controller, what you get is a dramatic reduction of performance. So here what's happening is that the reinforcement learning part is trying to explore too much and too soon, and is not letting the nominal strategy to do its work. And this brings us too far from the real strategy, the good strategy, and just fails. And interestingly, introducing recurrent elements by itself in this way makes things a bit better. So we can reach almost the performance that we had with only the impedance controller, but still quite bad. And the intuition here is that you have to get close to the goal to get stuck, or to find that you have not reached the goal, and then use the temporal information in your strategy. However, what you already see is that by introducing the decay without the recurrent part, we finally start to see some performance that are better than the bare impedance controller, but then only when we combine the two things together. So the decay to bring us close to the final goal, and the recurrent part to reason about time, about being stuck, and about how was before and I am now. That's the performance really get over 80% of success rate. What I think is also pretty nice is that if you look at the decay case and our final case, in both of them, the time needed to execute the task strongly decreases. And in our case, we get on average below half the time that it was requested. And indeed, if you play back the videos that I showed you before, you will see that for the impedance controller, there was a 2 times in the execution time, while the one with reinforcement learning were real time. So similar things, and you can see here the 1 pair to confirm what I just told you. Similar things can be done for insertion tasks with similar results. And also you can try to do more interesting things, still of the same kind, like inserting glasses on this in this rack. And also going back to our original motivation, play with the Ananoy tower. Of course, here we're focusing only on the insertion task, so the actual recognition and sequencing of the objects is hand-tuned, but the insertion is again similarly learned. Okay, so what we got here from what we got from this work is some understanding of how to combine reinforcement learning with virtual softness, so with impedance, and the fact that by doing that properly, you can learn complex interaction tasks with a few minutes of purely real-world experiments. The question now is, can we do better? And what we want to do is to try to see what we can do in terms of using more complex robotic hands, like the one that I'm showing here, more inspired by how the human hand works, and learn to perform more complex tasks like in-hand manipulation. And if you want to know more, apart from asking questions, writing emails, and the usual stuff, you can also refer to this paper, which is the official publication connected to this work, which is open access. You can find it by typing the name, looking in the journal, or by accessing through this QR code. Thank you very much for your attention.